In last class, we have seen line integral of a complex function. So, by line integral, we mean the integral along a curve, and we have seen two different types of line integral. That is, we have seen the integral of an analytic function and integral of non-analytic functions. So, for an analytic function, we have seen the integral will depend only on the endpoints. That is, if we find integral a to b f of z dz, that will be equal to the integral of f of z evaluated at b minus integral of f of z evaluated at a. But for a non-analytic function, the integral will depend on the path of integration. That is, even if a and b are the endpoints are the same, if you take two different paths from a to b, the integral of f of z will be different along the two different paths. So today we are going to see integral of analytic functions, integrals involving analytic functions in closed curves. So for a closed curve, we know the endpoints, the initial point and the terminal point will be the same. So this curve is not a closed curve because this is the initial point, this is the, if you put an arrow here, this is the initial point, this is the terminal point, they are different, it is not closed. But it is a and we say that a curve is simple if it does not intersect itself. So this is an open curve, it is a simple curve. This is again an open curve, not a closed curve, and this is not simple because it intersects itself at this point. Now when you come to this is a closed curve, it is a simple closed curve, and this is again a closed curve. You can reach at the initial point, the point where we start moving through this curve. So it is closed, but it is not simple if as it intersect at this point. So a simple closed curve is one which does not intersect itself. Now we move to some definitions on region in Z plane. So we say that as region in Z plane is connected if you can move from one point in that region to another point in that region without crossing that region. That is, if you start at this point, you can reach to any other point in this region without going out of this region. So this is a connected region. This is also connected because if you start at any point in this region, you can reach any other point without crossing this region. This is also connected. You can move from any point to any other point without going outside this region. This is also connected. Now we say that a region is simply connected if there is no holes in the region, or in other words, the boundary of that region will be a single curve. So if you look at this region, the boundary of this region is this simple closed curve. So a region bounded by a simple closed curve, we say that it is simply connected. Here also the boundary is a simple closed curve. You can move like this, and this curve does not intersect itself. So we can say the boundary is a simple closed curve. It is a simply connected region. And a region in which there are holes in that region is called a multiply connected region. So if you look at this region, this is a connected region, but there is a hole inside this region. Or in other words, the boundary of this region consists of two different curves. One boundary is here, this curve. Another boundary is here. So we say that it is doubly connected. And if you look at this region, there are two holes in this region. Or in other words, the boundary consists of three different curves. One is here, one is here, one is here. So if there are holes in this region, we say that it is multiply connected. So here we have three bounding curves. So we say that this is a triply connected region. Now we are going to see a theorem for the integral of analytic function, which is known as Cauchy's integral theorem. So we need these definitions while stating this theorem. The theorem says that if C is a simple closed curve, so it means that C is a curve which does not intersect itself, it is a closed curve, and f of z is analytic inside and on that curve. So f of z is analytic at all points bounded by the simple closed curve and also on the boundary points of the curve C. On the curve C, then integral over C f z dz is equal to 0. So Cauchy's integral theorem says that the integral of an analytic function on a closed curve will be 0. Now if C is not a closed curve, this needn't be true. Okay, so if C is a closed curve, what happens is if you find integral over C, the initial point and terminal point are the same. So we have seen in the previous class, that is the line integral of an analytic function is f of b minus f of a, where capital F of z represents the integral of small f of z. So for a closed curve, this b and a will be the same. The initial point and terminal point will be the same. So f of b minus f of a will be equal to 0. So if f of z is analytic on inside and on the curve C, then the integral of f of z will be equal to 0. This is called Cauchy's integral theorem. Now the same thing we can say in a connected domain, that is, suppose f of z is analytic. What we have said now was f of z is analytic inside and on the closed curve C. So if f of z is analytic inside a simply connected domain D and C is any simple closed curve in D, that means f of z will be inside analytic inside and on C, right? C is some region in plane, D is some region in plane and C is any closed curve in that region. That means the function will be analytic inside and on that closed curve if C completely lies within D. So then integral over C f z dz will be equal to 0. So the basic requirement to apply the Cauchy's integral theorem is f of z should be an analytic function. Second one, C should be a simple closed curve. Then the integral will be equal to 0. So in this case, this is using this theorem, you can reach at that statement which I just mentioned in the last class. That is, if you take an analytic function f of z and a and b are 2 points, if you take a curve C1 from A to B, another curve C2 from A to B, then integral from A to B, our condition is f of z is analytic in this region. So in particular it is analytic inside this closed region. So integral A to B f of z dz evaluated at C1 on C1 will be equal to integral from A to B along C2. So this you can easily prove using that Cauchy's integral theorem. That is, if you take the curve C2, C2 is from A to B, and reverse C1, that is, we take minus C1. So the direction will be reverse. C1 will be minus C1 will be from B to A. So if you take C2 minus C1, it is a simple closed curve, right? So C2 minus C1 is a simple closed curve and it is given that f of z is analytic in this region. So in particular f of z is analytic inside and on C2 minus C1. So using Cauchy's integral theorem, you can say integral on C2 minus C1 f of z dz will be equal to 0. Cauchy's integral theorem apply ചെയ്യാനായിട്ട് നമുക്ക് ഇത്രയും മതി. ഒരു സിമ്പിൾ ക്ലോസ് കർവ് ഉണ്ടാവണം. ആ സിമ്പിൾ ക്ലോസ് കർവ് ആണ് നമ്മൾ C2 മൈനസ് C1 എടുത്തിരിക്കുന്നത്. എയിൽ നിന്ന് തുടങ്ങി ബിയിലെത്തി മൈനസ് C1ലേക്കൂടെ തിരിച്ച് എയിലേക്ക്. അപ്പോൾ ആ സിമ്പിൾ ക്ലോസ് കർവ് കിട്ടി. ഇനി എഫ് ഓഫ് സെറ്റ് അനലിറ്റിക് ആണ്. So we can say integral C2 minus C1 f of z dz is equal to 0. And you can split the integral as integral over C2 f of z dz plus integral over minus C1 f of z dz. This will be equal to 0. So what we get is integral over C2 f of z dz plus integral over minus C1 f of z dz is minus integral over C1. നമ്മൾ direction reverse ചെയ്യുമ്പോൾ കിട്ടുന്നത് C1ന്റെ നെഗറ്റീവ് ആയിരിക്കും നമുക്ക് C1ലെ ഇന്റഗ്രലിന്റെ നെഗറ്റീവ് ആയിരിക്കും നമുക്ക് കിട്ടുന്നത്. So minus integral over C1 f of z dz is equal to 0. So here you can conclude integral over C1 f of z dz equal to integral over C2 f of z dz. So if the function is analytic, it doesn't matter through which path we go from A to B. If you take two different paths, the integral will be the same. So, and this we can see this will be equal to f of B minus f of A, where this f of B along f dash z is equal to f of z, or in other words capital F of z is the integral of small f of z. So integral does not depend on the path of integration if the function is analytic. Just evaluate the integral at the end points. You will be able to find the integral. So this is an immediate result of Cauchy's integral theorem. Now using that property, suppose we are going to find integral 0 to 2 plus I z square dz. Yesterday we have seen integral 0 to 2 plus I z bar dz along these two paths, along the line from 0 to 2 plus I and also along the line from 0 to 2, then 2 to 2 plus I. And we got different answers for both the curves or for both the paths. And I mentioned that this is because z bar is not an analytic function. So here we are going to find integral 0 to 2 plus I z square dz along the line from 0 to 2 plus I and also the line from 0 to 2, then to 2 plus I. So we are finding the integral of this function along two different paths. So we take 2 points 0 and here we have 2 plus I. C1 is this part, the straight line from 0 to 2 plus I. This is our first path. And in the second case, our path is the path from 0 to 2, then to 2 plus I. So we have in the first case this as our C. Second case we are moving from 0 to 2 plus I again, but along this path. So here the integrand is z square. So we are finding out integral 0 to 2 plus I z square dz. As the integrand is z square, we know z square is analytic everywhere. Every polynomial is analytic in the whole z plane. So Z square is analytic everywhere. So as Z square is analytic, you can integrate it just like a real function. So the integral will be Z cube by 3. So as it is analytic, you can say that the integral does not depend on path of integration. Right. So we just evaluate the integral, which is Z cube by 3, and we evaluate this value at the end point. So what we get is 2 plus I whole cube by 3 as the value of this integral. Okay, so you should mention these things. Z square is analytic everywhere. So the integral does not depend on the path of integration. So this will be the answer for for both the curves. So if you name this as C1 and this path is C2, along both C1 and C2, the integral will be equal to Z cube by 3 evaluated from 0 to 2 plus I, just like a real function. So you should check whether the function is analytic in the region where we integrate, and if it is analytic, integrate it just like a real function. Now so this is what we mentioned here. The integral is 2 plus I the whole cube by 3, and simplifying that using a plus b whole cube, you will get it as 2 plus 6i by 3 along any path from 0 to 2 plus I. So you needn't find the integral separately for path 1 and path 2. Just state that the function is analytic, and hence the integral will be equal to Z cube by 3 from 0 to 2 plus I. But if it is a non-analytic function, as we have done in the case of Z bar, you should find the integral along the first path. You should find the integral along the second path separately, and you can see that you get different answers for this. So now consider this question: integral over C 1 by Z plus 1 dz, where C is the circle, mod Z minus 1 equal to 1. So our question is integral of 1 by Z plus 1 dz along C, where C is mod Z minus 1 equal to 1. So first let us see what the curve C represents. So mod Z minus 1 equal to 1 is a circle whose center is 1, right? Z equal to 1 is the center, and radius is 1, so it will touch the origin and pass like this. So we get a circle like this, and this is our C. And we are going to integrate this function. So look at this function 1 by Z plus 1. It's a ratio of polynomials. 1 is analytic, Z plus 1 is analytic. Hence this will be analytic everywhere except when the denominator is 0. So except at Z equal to minus 1. So the integrand is not analytic at Z equal to minus 1. So the function f of z is not analytic. It's a non-analytic function at Z equal to minus 1. But here see, the point Z equal to minus 1 is outside C, outside the curve. So we can say that it is analytic inside and on C. Okay, f of z is analytic inside and on C. So in the previous case, Z square was an entire function. Z square singular points analytic points. That's why we depend on the check. ഇതിന് അനലിറ്റിക് അല്ലാത്തൊരു പോയിന്റ് ഉണ്ട് z ഈക്വൽ ടു -1. അപ്പൊ നമ്മൾ ചെക്ക് ചെയ്യുന്നത് ഈ പോയിന്റ് ഈ കർവിന്റെ ഉള്ളിലാണോ പുറത്താണോ എന്ന് ചെക്ക് ചെയ്യാം. അപ്പൊ ചെക്ക് ചെയ്യുമ്പോൾ നമുക്ക് കാണാൻ പറ്റിയത് ഈ പോയിന്റ് ഇതിന്റെ പുറത്താണ്. അപ്പൊ നമുക്ക് എന്ത് പറയാം, ഈ കർവിന്റെ ഉള്ളില് ഈ ഫംഗ്ഷൻ f of z 1/z+1 അനലിറ്റിക് ആണ്. ഇവിടെയാണ് അനലിറ്റിക് അല്ലാത്ത പോയിന്റ് വരുന്നത്. ബാക്കി എല്ലാവരുടെയും ഇത് അനലിറ്റിക് ആണ്. സോ ഇറ്റ് ഈസ് അനലിറ്റിക് ഇൻസൈഡ് ആൻഡ് ഓൺ C. അപ്പോൾ അനലിറ്റിക് ഇൻസൈഡ് ആൻഡ് ഓൺ C ആണെങ്കിൽ നമുക്ക് Cauchy's integral theorem അപ്ലൈ ചെയ്യാം. Therefore 1/z+1 dz will be equal to 0. C is a simple closed curve, so integral over C 1/z+1 dz equal to 0 by Cauchy's integral theorem. So Cauchy's integral theorem apply ചെയ്യാനായിട്ട് entire function ആവണമെന്ന് നിർബന്ധമൊന്നുമില്ല. അനലിറ്റിക് അല്ലാത്ത പോയിന്റ്സ് ഉണ്ടാവാം. അനലിറ്റിക് അല്ലാത്ത പോയിന്റ്സ് കർവിന്റെ പുറത്താണ് കിടക്കണമെന്ന് വെച്ച് കഴിഞ്ഞാൽ നമുക്ക് പറയാം ആ കർവിന്റെ ഉള്ളിൽ ഇന്റഗ്രൽ 0 ആയിരിക്കും. സോ ദിസ് ഇസ് Cauchy's integral theorem. Now see integral over C sin z dz. So if you take integral over C sin z dz, sin z we know it is an entire function, right? So it is analytic everywhere. So its integral will be 0 along any closed path. Plane like edukada ഏത് പാത്ത് എടുത്താലും ആ പാത്തിൽ സിമ്പിൾ ക്ലോസ് കർവ് ആണെന്ന് വെച്ച് കഴിഞ്ഞാൽ ഇന്റഗ്രൽ 0 ആയിരിക്കും. സോ ഇവിടെ നമ്മൾ എടുത്തിരിക്കുന്ന പാത്ത് എന്ന് പറയുന്നത് ഒരു സർക്കിൾ ആണ്. സർക്കിൾ നമുക്കറിയാം സിമ്പിൾ ക്ലോസ് കർവ് ആണ്. ഇപ്പൊ C is a path and in that C is a path in which the function sin z is analytic and therefore integral over C sin z dz will be equal to 0. ഇപ്പൊ entire function ആണെങ്കിൽ like sin z e raised to z, cos hz, sin hz, പോളിനോമിയൽസ്, ഇതൊക്കെയാണ് നമ്മുടെ ഫംഗ്ഷൻ എന്ന് വെച്ച് കഴിഞ്ഞാൽ കർവ് സിമ്പിൾ ക്ലോസ്ഡ് ആണോ എന്ന് മാത്രം നോക്കിയാൽ മതി. നോൺ ഇന്റർസെക്റ്റിംഗ് കർവ് ആണെന്ന് വെച്ച് കഴിഞ്ഞാൽ കർവ് എവിടെ കിടന്നാലും നമുക്ക് ഇന്റഗ്രൽ 0 വരും. അതേസമയം ഇങ്ങനത്തെ ഫംഗ്ഷൻ കിട്ടിക്കഴിഞ്ഞു കഴിഞ്ഞാൽ നമ്മൾ ചെയ്യേണ്ടത് ഇത് അനലിറ്റിക് അല്ലാത്ത പോയിന്റ്സ് നോക്കാം. അനലിറ്റിക് അല്ലാത്ത പോയിന്റ്സ് നമ്മുടെ കർവിന്റെ പുറത്താണ് കിടക്കണമെന്ന് വെച്ച് കഴിഞ്ഞാൽ ഇന്റഗ്രൽ 0 ആയിരിക്കും. വേറൊരു തരത്തിൽ പറഞ്ഞു കഴിഞ്ഞാൽ ക്ലോസ്ഡ് കർവില്, സിമ്പിൾ ക്ലോസ് കർവില് ഒരു കോംപ്ലക്സ് ഫംഗ്ഷന് നോൺ സീറോ ഇന്റഗ്രൽ വരണം എന്ന് വെച്ച് കഴിഞ്ഞാൽ അതിന്റെ ഉള്ളില് അനലിറ്റിക് അല്ലാത്ത പോയിന്റ്സ് ഉണ്ടായാൽ മാത്രമേ നോൺ സീറോ ഇന്റഗ്രൽ വരുള്ളൂ. ഒന്നുകൂടെ ശ്രദ്ധിച്ചു കേൾക്കാം. ഒരു സിമ്പിൾ ക്ലോസ് കർവ് സിയില് ഇന്റഗ്രല് നോൺ സീറോ വരണം എന്ന് വെച്ച് കഴിഞ്ഞാൽ ആ കർവിന്റെ ഉള്ളില് നമ്മുടെ ഫംഗ്ഷന്റെ സിംഗുലർ പോയിന്റ്സ്, അതായത് അനലിറ്റിക് അല്ലാത്ത പോയിന്റ്സ് ഉണ്ടാവണം. അനലിറ്റിക് അല്ലാത്ത പോയിന്റ്സ് കർവിന്റെ പുറത്താണ് കിടക്കണമെന്ന് വെച്ച് കഴിഞ്ഞാൽ ഇന്റഗ്രല് 0 ആയിരിക്കും. സോ ആസ് വി ഹാവ് സീൻ ഹിയർ z equal to -1 പുറത്താണ്, അതുകൊണ്ട് ഇന്റഗ്രൽ 0.